we are looking at the uses of dimension. One of the use of dimension is to check the uniformity of a physical quantity. The second is to derive the unit and dimension of a physical quantity. And third is to derive the exact form of a physical quantity. Well, let's take it one after the other now to check the uniformity of a physical quantity. Well, to check the uniformity of a physical quantity. For example, let me give an illustration now. Somebody one day derived this formula for motion, equation for motion, that V is equal to U plus AT. Now, when you derive a an a relationship that is used in physics, one of the tests to confirm if your relationship is correct, one of the tests it undergoes is the test of dimension. We use dimension to check. I could use this formula and get an answer. That doesn't mean the formula is correct. That doesn't mean the relationship is correct. It must go through dimensional test to check if it's homogeneous, if it's uniform. That's another word for homogeneous. Let me explain what I mean now. As we look at this now, there are three quantities in this relationship. The first quantity is V, the second quantity is U, and the last quantity is AT. Now, if this thing is going to be dimensionally correct, all of them must be uniform. They must be homogeneous. Mean that if I check the dimension for V, now V means final velocity, but in essence, it's just velocity, though final velocity. So, what's the dimension for velocity? Remember now, it is LT minus 1. The next one is U. What is U? U is initial velocity, but again, it is still velocity, though initial velocity. What's the dimension? LT minus 1. The last one now, which is AT, is acceleration times time, the last quantity there. Now, for acceleration, it is LT minus 2 now. Then times the last one, T, which is T. And then by the time we multiply this T is like T raised to power 1. By the time we multiply the two of them, it will become LT minus 2 plus 1. And this becomes LT minus 1. So everything has LT minus 1, the V LT minus 1, U is LT minus 1, and the AT eventually gives, when multiplied, LT minus 1. So they are uniform, they are homogeneous because they give the same dimension. That tells you that this relationship has passed a dimensional test. So it has passed dimensional test, then you use the solve equation to give you the right answer and all that. So one of the tests a formula undergoes is the test of dimension. Let's take example on this now. Okay, look at this example now. Verify using dimension analysis if the equation of motion x equal to ut plus half at square is dimensionally correct. When I look at this equation now, there is three quantities there. The first one is the x, the next one is the u, t, and the next one is the at square. We don't consider half because it's a constant, so at square. So let's check now. The x means distance actually, and distance has a dimension of L. Now we have ut. U is initial velocity and t is time. So initial velocity is LT minus 1 because it is velocity. Then times the t there, which is time. T is t raised to power 1. So by the time you multiply these two, you get LT minus 1 plus 1. And that will give us LT raised to power 0. And then t raised to power 0 is 1. So it becomes L times the t raised to power 0 is 1. Remember now, and that's L. And then we have at square. At square means acceleration times time square. Acceleration is LT minus 2, the third one. Then times time, which is t raised to power 2. And this will eventually give us LT minus 2 plus 2. And so this is LT raised to power 0, which is L. So at the end of the day now, these three quantities has L, L, and L. So it is dimensionally correct. Let's take example 2. Okay, example 2 says Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction of the force. Using dimensional analysis, show that this expression is correct or not. Well, I want to assume you know this Newton's second law of motion. But that's by the way, we have that force is directly proportional to rate of change of momentum Fv minus mu over t. And then we can introduce our constants and removing the proportionality sign, that becomes F is equal to K into mv minus mu over t. Okay, so change of momentum means final momentum minus initial momentum, and final momentum is mv, initial momentum is mu. And when we say rate of change of momentum, means that thing should be divided by time, and that's why we're dividing by time. But you see, K in the second law of motion, which is a constant, is equal to 1. Eventually, we just have it that F is equal to mv minus mu over, over t. Well, I'm going to solve this expressing it properly so it can give us the number of quantities that the F is equal to. I'm going to say mv over t minus mu over t. And so clearly now we can see that there are three quantities here. What are the quantities? The first one is F. The second one is mv over t. And the last one is mu over t. So those are the three quantities here now. Let's go now. What is the dimension for F, which is force? It is m l t minus 2. What of mv over t? You know m is mass now, which is m. Dimension is m. V is velocity now, which is lt minus 1 now, over the t there time. This will now become m lt minus 1, and the 1 at the bottom goes up to become another minus 1. And so that will give us m lt minus 2. And then again, mu over t gives us again m is mass m, u is initial velocity, which is tlt minus 1, over time, which is t. Eventually it will give us the same thing as the previous one, which is mlt minus 2. So these three has the same dimension, and so we can say they are uniform. So another use of dimension is to derive the unit and dimension of a physical quantity. Okay, so I'm going to explain this now using some examples now. So let's take our third example under this now. Example 3 says we are looking at to derive the unit and dimension of a physical quantity now. So example 3 says the specific heat capacity of a metal is given as C is equal to AT cube at a temperature close to 0 Kelvin, where C is the specific capacity of the metal, T is the thermodynamic temperature, and A is a constant. Derive the unit of A in terms of the base unit in SI, and S state the dimensional value. Well, the first thing we want to do is to say, I want to turn the question. I want to get the dimensional value first and then the SI. It's easier that way. So the first thing I want to say is that we have that C is equal to AT cube. And so with this now, I'm looking for A. Simply make A the square of formula. A is equal to C over T raised to power 3. Very simple. But remember again, what is C? C from the question is specific heat capacity. Now, what is the dimension for specific heat capacity? It is given as, for specific capacity, is given as L square T minus 2 and then theta raised to power minus 1 all over. Now, we have T here. We are told that T is temperature, and that's theta, then raised to power 3. Eventually, the dimension becomes L square T minus 2 and theta minus 1 and then minus 3. So this gives us L square T minus 2 and then theta minus 4. This is dimension for A. This is dimension for A. And from this, we can get the unit, the SI unit. For the SI unit now, which is the base unit they ask us to get in SI unit. So for SI unit of A is simply going to be this L, remember, means length in meter. So that will be meter square. T means time, and that is seconds. Seconds S minus 2. And then theta means temperature, and that's Kelvin minus 4. So the unit will be m square x raised to power minus 2 and then K Kelvin raised to power minus 4. That's the SI unit. So we are done with this question. Example 4 says, what is the SI unit of K so that the equation velocity is equal to K times density is dimensionally correct? Well, solution now. We have velocity is equal to K times density. Well, for velocity now, we know the dimension for velocity. First of all, let's make K the square formula. K simply will be velocity over density. The equation can just be paraphrased to say find the dimension for K. Simple. So velocity over density, that's just what K is if you make K solid the formula. Now remember, velocity is m L T minus 1. And then density is m L minus 3. And so we can start now. M cancel out m. And then we'll be left with L on top raised to power 1. And there's L minus 3 up beneath the denominator. When it goes up, it becomes L plus 3. So that is plus 3. And that L plus 3. And then T minus 1. Eventually, this just L raised to power 4 and T raised to power minus 1. And so that's just the dimension of K. Let's take the last example under this second use of dimension. Okay, for this question, we have that it says in the van der Waals gas equation, P plus A over V square in brackets multiplying under 1 V minus B in brackets is equal to RT, where P is pressure, V is volume, and T is temperature. What are the dimensions of the constants A and B? Well, this is a very easy one, but I want to explain now this question. Right here, we are seeing two things. Let me rule a line. We are seeing the first one, P plus A over V square. And then V minus B. You see, like we said, if a formula is correct, then every term must have the same dimension. So this van der Waals equation has been proven to be dimensionally correct. That's what we are saying. And so every dimension you are seeing here is actually correct. It means that P and A over V square must have the same dimension. It also means that V and B must have the same dimension. That's just it. And so right here, what are we going to, each of the quantities in that relationship must have the same dimension. That what we say that is homogeneous. And so right here now, P means pressure. What's the dimension for pressure? Very simple. It is M L minus 1 T minus 2. And it should be the same thing as A over, we are looking for A. We don't know what A is, but it should be the same thing with A over V square. But we know what V is now. V is volume, which is L cube. But that volume has square. So we'll put our square here. And so we can now say this is M L minus 1 T minus 2 is equal to A over L raised to power 6 when we open up this bracket. Eventually, if we cross multiply this now, we get that A is simply equal to M, then L minus 1 with plus 6 because you are multiplying now, and then T minus 2. So this is simply M L minus 1, sorry, M plus 5, sorry, 5. Let me correct that. So M plus 5 and then T minus 2. And so again now, V and B, for them to be dimensionally correct, V means volume and B, so we can say volume LQ is same as that of B. So that's all. So B has a dimension of LQ and A has a dimension of ML raised to power 5T raised to power minus 2. So that's that about that. So we're looking at the third use of dimension.